So today I'm going to speak to you about why a 4-level laser can be more efficient than a 3-level laser, and also the difference between non-radiative and radiative transitions. So first we're going to talk about what we need to make a laser and how we actually get 3 and 4-level lasers. The first thing we need to discuss is how do we actually make a laser. Thinking about how the word laser is actually an acronym for light amplification by stimulated emission of radiation, we know that we need stimulated emission. So how do we get that? If we have an atom already in an excited state, as we can see here, then we have a photon coming in with an energy equal to the energy of the separation of the two energy states, delta E. The photon will cause the atom to move from an excited energy state to a lower energy state. In this process, it will emit another photon with an equal energy to that of the incident photon. So we know how to get stimulated emission, but for our laser we need this to be the most dominant process. So is there any way to make the stimulated emission the most likely process to occur? The answer is yes, and it's by using what is known as a population inversion. In normal situations, such as thermal equilibrium, you would expect to have the majority of the atoms in the lowest possible energy state. Therefore, as the name suggests, this is an inversion of a normal situation. We now have more atoms within the excited energy state than in the lower energy level. Okay, so I know you're thinking, why did I say we're going to look at 3 and 4 level lasers? Why can't we just have a 2-level laser? And the answer is, in theory it is possible, but in reality it's not. This is because all the energy being used to excite the atoms into the excited energy level has an equal probability of stimulating them back down, so we wouldn't have the population inversion that we need. Best case scenario would be to have an equal number in the lower energy state and the excited state, which is not what we want. So now we understand the general process of how to make a laser, and we've seen that it's not really possible to make it with a 2-level laser. So now we'll consider the 3-level laser. So from this diagram we can see the difference is now we have this metastable state in the middle, but our excited energy level is still higher than this. So first we need to excite the atoms into this excited energy level, but one important thing to note is that this excited energy level must have a shorter lifetime than that of the metastable state. So now the atoms drop down quickly to the metastable state in what is known as a non-radiative process, which I will explain in a minute. Once the atoms reach the metastable state, they begin to accumulate here because the metastable state has a much longer lifetime, which means we get the population inversion we need between the metastable level and the lowest energy level, which would have had the atoms in it excited already. So as I explained before, this population inversion means stimulated emission is now the more dominant transition, and therefore we have the laser transition we need. Now I mentioned something called a non-radiative process. This happens between the excited state and the metastable state. It basically means that the energy is released but in the form of heat. Now between the metastable state and the lowest energy state we have what is known as radiative process, which I called a laser transition before. This just means that we have a transition between the two states with the release of a photon with an energy equal to delta E, which is the energy difference between the two levels. This is stimulated emission, which we saw earlier. This stimulated emission basically empties the metastable state and repopulates the lowest energy state, so the process can start all over again. So now we're on to the last part of this presentation, and that's describing the 4-level laser, which we can see here. Now you'll notice that it's the same setup, but now we have a lower laser level, E2, between the metastable state and the lowest energy level. Now looking at the process, we can see that again the atoms are excited to the highest energy level, where they drop to the metastable state, E3. Here, however, we have the laser transition taking place between the upper and lower laser energy levels. Then the atoms eventually lose their excess energy and return back to E1, the lowest energy level. So you're probably still wondering why we would want the 4-level laser rather than the 3-level one. This is because the key difference with the FourLevel laser is that the lower laser level is not the same level as the lowest energy level, which we saw with the 3-level laser. If we look back at the 4-level laser diagram, we can see that the lower laser level has its own energy level. This means that at the beginning it won't have any atoms in it, so we get the population inversion we need immediately. With the 3-level laser, we need to excite most of the atoms out of the lowest energy level, so that once they reach the metastable level, there would be more in that level than in the lowest energy level. So that is why you would use a 4-level laser rather than a 3-level laser. Thank you for listening.